I think most people are back from coffee, so I just wanted to quickly introduce myself. I'm Patrick Ingram. I'm the Deputy Director here at Fields, and I just wanted to say a few words of welcome. I know this morning you already received the sort of logistical welcome and so on, so I want to just keep my comments very brief so that you can get on to the mathematics. So we're very happy to have this workshop here. We're very happy to have the focus program in algebraic topology in memory of Fred Cohen here. I want to say a few words about the Institute. Many of you are probably familiar with the Institute. Some of you maybe not so much. So the Fields Institute is funded by the province of Ontario and several principal sponsoring universities and NSERC and NSF. And we use that funding to promote fundamental and applied research in mathematics by bringing people together in what is hopefully an inclusive and inspiring environment for you to work together on math and so on. And so we do try to sort of keep it as an inclusive environment. If you have any concerns about anything from the temperature of the room to anything else, please come and see me. So I'm upstairs in room 320, and I'll also try to come by the coffee break and so on to say hi a little informally. But if you have any concerns or anything, please come see me. And the director, Deirdre Haskell, will also be around a little bit later in the week. So please come and seek us out. And I think those are all my remarks. Are there any questions about the Institute before we pass things on? My key message I wanted to make, since I think a lot of the logistical stuff happened this morning, was just if you have any concerns about anything, sometimes this room gets too hot or too cold, please come and see me, and we'll try to sort those out right away. So without further ado, I think I'll hand it over to the chair of the afternoon session, or organizing.
First of all, before we start, did anybody lose their phone? Excuse me, can I give this to you? Somebody left it in the toilet.
Oh, okay, yes.
Right. So after getting this out of the way, it's my pleasure to introduce somebody I know for almost as long as I've been a mathematician, Jesus Gonzalez, to tell us about square section braid groups.
So thank you very much. Is the microphone already? Yes. Fine. Okay. Perfect. You have to put on? Yes, it is. Yes. Right in here. So I switch it on. Okay. Can you hear me? Online. Online? Yeah, great, perfect, excellent. Well, thank you very much, Ran, for the kind invitation and the introduction, and special thanks to the organizers, that includes also Ran, for this nice invitation to give this talk. It's a real honor for me to be in this place, remembering some things about work that Fred did. And also special thanks to Shmuel for accepting me, for swapping my place in the talk. So, okay, without any further ado. So I'm gonna be talking about braid groups. Actually, I'm gonna be talking about a primitive version of these objects. So braids are important in many areas of mathematics, as we all know, but also they are important in outside mathematics, in other areas of science. And actually, I'm going to be introducing the ideas that I want to discuss in this talk by in this language of physics, namely statistical mechanics. And so, okay, so let me just very briefly, very informally and basic level. So let me just recall for you what a phase is. Well, matter in universe, recall that it comes in phases, like solid, liquid, or gas, or just to name the most popular ones. So what is a phase is an organization of the particles of a system that is characterized by a balance between the energies of the system, namely kinetic, potential energies of the particles. So this, of course, the nature prefers to stay in the most economical in terms of energetic way of speaking. Now, this balance can be altered when some energy coming from the surrounding environment affects this system, and then matter has to change phase. So this is where phase transitions happen there. And well, physicists have developed this beautiful theory of topological theory of phase transitions. So what's as the name suggests, this is the aim of this theory is to explain in purely topological terms the nature and the dynamics of phases and especially phase transitions. So, so the idea is that if you have a system of particles in some phase and with some given minimal value of the energy, all possible configurations of these particles with the same energy, namely this level submanifold, the topology of that can be considered as a signature of the current phase that the system is. And just as normal people, phases would have several signatures, several topologies associated. But basically, the changes in these topologies will be minor. But what physicists have proved is that topology changes coming from actual phase transitions are major. And they have several ways to detect them and to classify them. You can classify them by the order, namely the continuity of the derivatives of the higher first, second, and higher derivatives of the free energy function. For instance, in the most popular one, perhaps in boiling water, this is a first order phase transition where entropy, volume, changes abruptly precisely at the transition point. So as a topologist, my goal would be to understand, that would be rather a dream, to understand, to measure, to understand in some way these topology changes, and so to have a way to recognize or classify phase transitions. So I'm going to be doing this in the talk. I'm going to be discussing these topological signatures of phase transitions and of phases and phase transitions for a particular system. Namely, this is going to be the system of hard disks. This is a popular model in physics. Physicists have studied this model and used this model for more than 50 years. And well, so this is in this slide, I'm going to focus on this particular space. This is a configuration type space. So the U here stands for unlabeled, unordered. This is there is also a version that is ordered, but let me just stick to the most natural context in physics. Unlabeled configuration spaces of disks. Particles are not going to be point-like elements of a space, of a manifold. They are going to be actual two-dimensional disks. And the only thing that I'm going to be asking about them, requiring about the, the only thing that I'm going to be requiring about these hard disks is that they are hard. Namely, this is a term coming from physics, but for us, it only means that they do not overlap. They can touch it, they can bump into each other, touching their boundaries, and touch the region where they are contained in. So here, I'm using R for some bounded region in the plane, and I have then n hard squares of disks, n hard disks in the plane in some bounded region, and they have some fixed, all of them have some fixed radius R. All right, so let me just stress that this is a two-dimensional model. There are, of course, higher dimensional versions and other variants, but I'm focusing on this one because obviously I want to talk about Bray groups. And because, not because of the topology of these things is easy. Actually, this is really very complicated. I'm going to say a few words about that. But they are actually used by physicists to design and study the properties of thin films, and also to understand in material science, for instance, to understand the dynamics of interfaces between materials. But anyway, so back to the topological world. We can use these spaces of hard disks in some bounded region to, in a persistent topology perspective, using a persistent topology perspective. Namely, notice that these spaces are make this nested sequence of inclusions. Namely, if one has a configurations of n disks of radius r in some bounded region, then just shrink a little bit the radius, and you will have another configuration of n disks, smaller ones. So this way you can get an inclusion and then have this sequence of inclusions. Now, well, we can study changes in topology, of course. Physicists use this model with several techniques. But first of all, let me just say a few special characteristics of this system. Namely, physicists think of this as an athermal model because there is a lack of intrinsic energy levels for the configurations. Namely, here configurations only have two potential energy levels. Either a configurations of disks have infinite energy when two disks overlap, and I want to forbid those configurations, or the configuration has zero energy. So in this sense, we only have one level submanifold, namely the full configuration space of non-colliding of hard disks in some bounded region. Anyway, we have a continuous parameter given by the radius, and it plays a role of a temperature. Namely, if you shrink the disks, essentially you're modeling a system with higher kinetic energy, where particles can move in a wider ways and actually get closer to each other. All right, so physicists have used several techniques. They range from large computer implementation simulations using a Monte Carlo algorithms to sample these spaces to actual lab experimentation. And what they have found is that these spaces, the study of the topology in this sequence, they found that there is no difference between liquid and gas phases characteristics. So there is one single phase, which is the majority of the time it's this phase. And there is only a very interesting a melting process that goes from solid to gas, actually. Well, gas liquid, the same. But it uses an actual intermediate phase. This is the hexatic phase that the physicists use this word. Essentially, in this phase, disks can drift, but the bonding neighboring particles make angles of pi/3. So altogether, it make a pattern, a symmetry of hexagonal symmetry. And most importantly, this hexagonal symmetry decays slowly with distance. This is the one of the main characteristics of this intermediate phase. I'm going to be using this word in what I want to describe because the results that I'm going to report fit into this picture. Now, the thing is that these spaces are hard to understand. They are real spaces. And just to name just a very basic property about whether these spaces are connective, they are not. Count the number of components. Well, if you look at the number of components, that's not a monotonic function on the radius. So if you start increasing the temperature at decreasing radius, all of a sudden new components start arising. So this is kind of a mess. So as an alternative, now this is the point of the talk, one introduces, well, this is an idea of Hannah Halpert. One replaces the Euclidean metric given disks by the L-infinity metric given squares. So I'm going to be looking at square particles, squares. And the other modification is that in the case of disks, one has a varying radius to study topology transitions. Now, I'm going to insist that these squares have a fixed radius, say 1/2, so that my particles are going to be unit squares of side 1. Instead, I'm going to replace this parameter, temperature-like parameter given by the radius in the case of disks by two parameters, P and Q. These two parameters. Namely, these are going to be the size of the huge rectangular container where these non-colliding hard squares are going to be living. And now I can vary these two parameters and to understand then the dynamics of the changes in topology of these spaces. So quite easily one can understand the topology of a few examples. For instance, the largest number of squares that I can fit in a P times Q rectangular shape is precisely P times Q. And for me, this is going to be the actual real solid state. Yeah.
You write disks and you say squares.
Sorry, now it's squares, but I'm replaced disks. So I'm not using UD, I'm using UC now is for squares.
Okay.
So the rest of the talk is gonna be just for squares. But you're right, sometimes I get confused and I say something that I didn't want to say.
We all do.
All right, so for instance, we can immediately limit n to be at most pq minus 1. P and q, by the way, are integers. They don't have to be. It would be more interesting that they are real numbers, but the techniques that I'm going to be used are discrete. And well, I'm going to stick to this condition. So, well, some other cases are contractible, and this is essentially the range of interest that if you think a little bit, you will see that these spaces behave like that. Now, the point that I want to bring to say from all this discussion is that these hard square configuration spaces also have no distinction between liquid and gas on the one hand. And the melting process also involves an intermediate phase. Now, this is called a tetradic phase. And essentially it plays the role of the hexatic phase, but instead of like an hexagonal symmetry decaying slowly with distance, now it's a fourfold symmetry. And you can actually more or less see it on the background image of these slides. All right, now these spaces have already been studied recently by a number of people. And one of the papers that I want to just mention briefly is this one by Halpert, Bauer, Kale, McPherson, and Spendlove of a couple of years ago, where they actually, well, one of the things that they prove is the homotopy dimension. They give an upper bound for the homotopy dimension of these spaces. And they also use homological methods to see that basically up to a little on code, a little modification on the upper bound, you can find homology in all possible dimensions. So, but still, a lot of things are not known about the homology of these spaces. Are there a global, what is the global description? Either knowing for n, p, and q given, what are the cases where homology is trivial or non-trivial? This is really not well understood. Even a question as basic as understanding torsion, and even in the order situation, is not known. And well, you can compare this with what happens in the classical pointwise situation. Okay, but this is not a talk about homology. I'm not going to be using homology for understanding the persistent topology of this model. So let me back to topology to actually give you some kind of the idea of the definitions of these phases that I want to work with: solid, gas, and the intermediate ones. So, well, there is an obvious candidate for a solid topology when you have the maximum number of unital squares fitting inside a rectangle. So that's, for me, this is the only topology that is solid. And then I can use, remember this sequence of nested inclusions. Well, the limit of that is basically the usual, the standard classical configuration space of unlabeled points in the plane. Namely, if you have a configuration of n squares in this rectangle, you can just take the barycenters of the squares. They are not colliding. So in particular, the centers are different. So you get a honest configuration on this side. And it is known that this horizontal inclusion is actually a homotopy equivalence if the sizes of this rectangular container are large enough, at least n. So that gives me a way to understand what would be an ideal gas phase for these spaces. Namely, whenever this condition holds and the rectangle is at least n by n or higher, then I would say that that topology is an ideal gas topology. All right, but then this is what happens when you increase both P and Q. But the point of this talk is that I want to make a difference. I want to increase P as long as I keep one of the parameters fixed. Say Q, the height of the rectangle, is going to be kept fixed, and I'm going to be increasing P. So when I do this, in the limit, I get this space that is essentially configurations of n hard squares, living inside an infinite horizontal strip of high Q, the fixed Q that I kept. And this is also an equivalence in certain range, which gives me the Q gas topology. I just call it that way. This is the Q gas topology. And then I can start increasing the parameter Q to get all the way down to here. And this is also a homotopy equivalence in this range. So the idea here is that you start with squares, and then when you move the width of the rectangle where they live, essentially the squares start becoming thinner and thinner. And in the limit, you get only slender particles, vertical particles that move on an infinite strip. That would be the Q gas topology. And then you start increasing the height. And well, this is equivalent to saying that your slender particles start shrinking and shrinking and shrinking until they behave up to homotopy like actual points. So, okay, this is the preliminary stuff. So let me start reporting some new results in this direction. Well, phase transitions on this side have already been studied by homological methods by Manin and Alpert. But again, I'm not going to be using homology. The proposal here, because of the title of this talk, is use fundamental group. Go to fundamental group to see what happens. So I'm going to be taking fundamental group of these three spaces. Somehow I change. Yeah, so I'm going to be changing fundamental group, taking fundamental group. So I call Bn P times Q this break type group, but where strands can only move in this rectangular shape. Likewise, BNQ would be the fundamental group of that, and the classical one, Bn. So this is Artin's break group, classical with n strands. So I want to describe then what happens in these phase transitions, and then what happens in these phase transitions at the level of fundamental groups. And so let me do that by recalling very briefly what is the description of this fundamental group, because recall that this space is spherical, so everything is concentrated in the fundamental group. And this space has finite presentation, is finally presented. It has n-1 generators. And these generators satisfy two types of different relations. There is, on the one hand, the right angle type relations, basically saying, well, our generators commute among them as long as they have indices that are not consecutive ones. So good, so far so good. And then what happens with the consecutive ones? Well, they satisfy this break type relation. This is the relation really responsible for the braiding behavior in these groups. So now the first result is what happens is about these phase transitions. Well, the result says that, and this was actually known in this case, in this particular case, this was known to McPherson and their collaborators, that this is a two equivalence. It's a homotopy equivalence up to dimension 2. Therefore, it is an isomorphism in fundamental groups. So the fundamental group of this thing is just the braid group, as long as the height of the infinite strip is 3 or more. However, at height 2, here, something different happens, and this is quite interesting. You only have one equivalence of the homotopy, and the map is only surjective in homotopy groups. And it is not injective, and the kernel, guess what? It is generated by the braiding relations. So essentially, the fundamental group of this guy at height 2 is just filtering away the braiding relations, and just you keep at the end a right angle arcing group, essentially. And this right angle arcing group is determined by this graph, of course, where you have n-1 generators and everything commutes with everything. So this is a complete graph, but the immediate ones. So you have to remove a maximal linear tree. All right, so this is what happens on this side at the fundamental group level. So let me tell you what happens on the other side once I am fixing the height and then increasing the width of the rectangles. And of course, if I'm going to tell you first what happens at height 2, because here I have filtered away the braiding relations. All right, so here's what it happens. And this is just the reason why I started discussing about these things, about the tetradic phases and so on. Namely, all the inclusions, so notice that here, all the spaces live in rectangles of height 2. This is the special situation. I'm increasing the width of the rectangles. I'm keeping the number of particles of squares. And all these inclusions turn out to be isomorphisms. They are a little bit strange isomorphisms because they are given by conjugation. They are very subtle descriptions, but you can actually prove what these morphisms are. And these are conjugation type isomorphisms. And they are all isomorphisms in this range. Namely, basically when P is at least half of N, basically. And this improves my definition of the gas type topology. It essentially drops down to 2. But most importantly, it only leaves 4 special cases outside this range. And this is what I would call the tetradic, potentially tetradic, at least to under the glass of fundamental group, the possible tetradic phases. And notice there are at most 2, but recall, since N is fixed, I'm fixing the N in this process. Of course, out of these 4, only 2 are relevant depending on the parity of N. So if you do a little bit of arithmetics, you will see that fixed N, when P is 1 more than roughly half of N, this would be the first tetradic phase. And the next one would be just increase one side to the right, the base of the rectangle. That would be the second potential tetradic phase. These are actually different in many cases I'm going to be reporting. And for higher P, you will be in the range of the theorem above. Maybe this would be just the gas topology. And below that, namely when P is roughly half of N, this will be the uninteresting solid case. So let me tell you what happens. Let me tell you what happens in the first tetradic phase. So of course, this depends on, yeah, this is the one. Yeah, this is the one. It depends on the parity of N. It might be odd or it might be even. And the thing is that these spaces are spherical, turn out to be spherical, only in these 2 cases that I know of. There are some results that are, I guess, are not published by Plachta that said that in general, you would not expect to have aspherical spaces. But in these 2 cases, you do have spherical spaces. So it's a matter of computing the fundamental group. And in this case, it's free non-abelian, of course. So this classifying space is just a wedge of circles. And this is the first one that is quite interesting. Namely, it is again, no surprise, it should be a right, well, morally, it had to be a right angle arcing group because the gas thing was the right angle arcing group filtering away the braiding relations. But the graph that describes this as a right angle arcing group, as a RAG, is described in here. It has 3 isolated vertices. This takes into account possibly the case where P is 2, but think of this as 3 isolated vertices. And then it has P minus 3 vertices on top, P minus 3 vertices on bottom, and a bunch of edges, making this bipartite graph. Here are some explicit examples, but the thing here is that being this a RAG, its classifying space is given by a polyhedral product, a polyhedral power of the circle. Essentially, what you're doing is think of this polyhedral power for this graph. Notice that this graph is bipartite. So it means that the flat complex is just a graph. So there's no scene in here. And the thing is that this space is just, again, a wedge of circles, as many as vertices there are in here, namely 2p minus 3 if you count, except that you're attaching little tori on top of 2 vertices of 2 wedge circles that support one of these edges. So this is a Salvetti type model.
Question. So is that a torus only, or you need something else there?
This is
It's
a polyhedral
product.
So what
is the EP minus 3?
this is this graph. EP minus 3 is a graph. Is bipartite. So the flat complex is that thing, and you're doing just the Salvetti model. But in this case, it's just what you see. You don't have to fill in triangles. And so this is the kind of torus I was saying. This is the kind of torus S1 crosses 1 attached to S1 wedges 1 for each pair of vertices that share an edge. All right, so the point is that this is a primitive version of the graph defining the right angle essence of Artin's ray groups, right? Now, this is what happens in the first tetradic phase, topology or phase. So unfortunately, I cannot report just yet what happens in the second tetradic topology, at least under the class of the fundamental group. But the slide that you already saw, it gives you a summary of what I know in some low level cases about the these are computed to be RAGs, and on the bottom you see the graphs defining these RAGs. Sorry about that. Okay, but I might not have much time, so I'm gonna skip this description. This is kind of it doesn't shed much light into the picture because it's just computational. But if you are interested, I can just go back and tell you about these things, about this second tetradic topology and overall the Q melting process. All right, so let me, what we've described then is the 2 tetradic phases in this melting process of hard squares in height 2. But what about higher heights, at 3 and higher? Now things are going to be, in principle, more complicated because now we have to take into account the braiding things that were kicked out at height 2. All right. So here's what happens, what I can report on about height 3 or higher. There are some conjectures, some naive conjectures of the discussion that I already gave about what you could be hoping for tetradic phases, how long does it last, and so on. But let me just report on this result that, again, it's in the case of aspherical cases, spherical topologies. And the first two, these are the first twos in the sense that n is congruent with with -1 or -2 mod q before q was 2. And the first tetradic topologies. So the very first one, namely when n is this number, is again, this is quite easy to see. This, you can actually compute this fundamental group. It's free. So the corresponding space is just a wedge of circles. However, for the second topology, this one, things are a little bit different than one would expect. Namely, recall that at height 2, we had a RAG. The fundamental group was a right angle arcing group. Now, it is perhaps, and it is certainly in some cases, not a RAG, but still this group is a simple commutator-related group. Namely, it has a finite presentation with some generators, some relations, but the point is that each relation is a commutator, not a word on commutators. It's actually a commutator. The tricky part is that the factors of each one of these commutators are not generators necessarily. They can be words on the generators. If they were generators, this would be a RAG, and it would be simpler to understand. So this is a simple commutator-related group, but it still is very efficient. I can give you, it's complicated. I'm going to give you a picture that summarizes the description. But this is a very efficient description in the sense that it has as many generators and relations as the two first Betti numbers of its corresponding spaces, just as the RAG, as it happens at height 2 with the RAG description. And not only that, but the homology in these two cases is torsion-free and is concentrated in those 2 dimensions. The thing is connected. So the question, natural question is this an actual RAG? It looks like. Maybe in any time that you have a group that is simple commutator related, namely relators are commutators, well, look at one of the factors of the commutator. It would be a word, but then you can make Titze transformations to say, well, for me, this is a new generator, and maybe you make a change of basis, and you are lucky enough to distinguish a RAG. And indeed, this is what happens at height 2, and you recover the situation at height 2 precisely that I have reported. But in general, and in particular, at height 3, you do not get a RAG. You almost get a RAG. So you get what is called in group theory, in geometric group theory, a HNN, Higgs Neumann extension of a right angle arcing group. So let me just recall for you very briefly what is a HNN extension of a group. So you essentially have your base group, and then you want to put it inside another group, larger group, just by adding one element. And this element essentially is picked so that it conjugates some given subgroup into some other given subgroup. You're just extending, but 2 given subgroups are being declared to be conjugated one from the other. So this is what really happens in here. This space at height 3 in the first tetradic topology in this congruence, mod 3, is a right angle arcing group of this graph. I'm going to say a few words about this graph with an extra generator. Now, I've given this picture. This picture is in the case where P is 8, which is the first complete example that exhibits all the features of the general description. So this graph is this square, or should I say a meta square. Namely, recall from the previous description, this graph that I called E of P minus 3 that has P minus 3 vertices on top. Let me call these P minus 3 vertices a meta vertex, then a meta vertex on the bottom, and a meta edge. All the edges making up this bipartite graph. So this is just for me, this is a meta edge. Well, it turns out that the description of this graph is nothing but a meta square. It has 4 meta vertices and 4 meta edges, forming this particular God-given graph, which is responsible for the commutator relations among the given generators corresponding to the vertices. And except that it has two additional edges, like shown in here, that come as follows. Well, it is not fully a rack, namely it's this thing, but then you have an extra element. And this extra element conjugates some of these elements on the left into some of the elements on the right. In this case, when P is 8, it conjugates the first two on the bottom into these first two, and then the first two on top are conjugated under B on to these other guys, to the last two, like in here. And for instance, this purple edge is coming from the fact that if you look at Y3 and Y3 prime, I hope you can actually see that, they share a line, so they commute. And therefore, they conjugates commute, but the conjugates are precisely X1 and X1 prime. So you have some extra commutation relations forced on you just because of this HNN extension. But anyway, the point is that once you compute this fundamental group, you use Hatcher's book, for instance, just to realize what's a geometrical way to construct this classifying space, because this space is aspherical. And essentially what you do is, well, you start with your rack, your base rack. So you start with the Salvetti complex associated to this graph. This is still bipartite. So you see only here a bunch of wedges of circles and some little torus in there. And then you take this subgraph consisting on these three elements and the other three elements. This is the complete subgraph on the left. And you take the complete graph on the right. And you put, they are isomorphic through B precisely, and make a cylinder. And one side of the cylinder is glued into this subgraph, and the other side of the cylinder is glued on the other side. So at the end, this space already has a torus type description, but it's not a bunch of little tori. It's a mapping torus that you are actually attaching. And the section of this mapping torus is, of course, also a Salvetti complex. All right, so I'm basically complete. So let me just finish by giving some final thoughts on this kind of idea. So I haven't proven anything. And the reason for doing that is because it's not so very pleasant to show you some computations, because these are hard computations. Essentially, what is in the back of all this is that, well, these hard squares systems have the homotopy type of cubical complexes. And this is what's proven by Matt Cale and McPherson and their collaborators. So you have these beautiful cubical complex. And then, well, you want to compute the fundamental group, and you can do it a la Poincaré. Just take one-dimensional skeleton. Those are collapse a few of them just by taking a maximal tree. But what you're left with are actual generators, and you just take, then out of this cubical complex, you only take two cells, and those are going to give you your relations. The point is that this is huge. This model is huge, even in the unordered case where you're dividing by the action of sigma n. This is huge. So you don't really want to do that because that's not doable. So essentially, well, anyway, you produce a discrete gradient field on this cubical complex. And it actually is closely related to a classical gradient field, namely this cubical model of the homotopy of these spaces contains Abrams's discrete configuration space of graphs somehow. Not gonna get into detail, but in that configuration space, discrete configuration space, there is Farley-Zavalka's gradient field, and then you can just use it, add a few extra two-dimensional cells, and then just use Poincaré's method, but Well, it would be Poincaré's Morse Foreman method of computing only in terms of critical cells, one-dimensional generator and two-dimensional generator. All right, so that's more or less what is on the back of this. And lastly, let me just present this idea that I actually learned from somebody that was around here, Luigi, that I met in Miami last week at another conference. In a conference, Miami, yes. And it has to do with homological stability. These spaces, from the computations that I've already described, these spaces are bound not to have homological stability. Namely, the problem here is that we're adding extra points. And we are not adding extra points to a manifold, say open manifold or whatever. We're adding actual squares. And when you do that, you alter the packing fraction and the topology spoils down. But still you can add more squares to keep the packing fraction. And in those terms, there would not be homological stability either, but there are chances because of the computations that I described that are higher homological stabilities. Namely, the difference between two consecutive things might somehow stabilize. That's something that I just learned from Luigi last week, the possibility of doing this, but I think this is an interesting project to consider. So thank you very much.
Are there any questions?